Okay, now the recording is started. Our subject is subsonic compressible flow over airfoils. Let's start watching it together.
Before starting with this topic, let me give you a brief review about what we have done so far in Aerodynamics 2 classes. First, we started with a brief review of thermodynamics because we said that energy transformations are important in the field of compressible flows. Then we continued with the derivation of shock wave and expansion wave theories, and later on you saw 1D nozzle flows, and now we are coming back to flow around airfoils, and I will try to come up with an equation that will once solved, that will give you some idea about flow over airfoil in subsonic compressible flows. Well, already you can see from the heading that we have linear theory as well here, because you will see in the coming slides that the final equation I will end up with will be a non-linear, but we will linearize it, and under some assumptions, of course, as we did for the incompressible flow cases, we will linearize it, and then we will have some solution for some given range of flows. Okay, so I will try to use the potential flow theory again, and then I will try to derive one equation that will be a combination of conservation of mass, conservation of momentum, and conservation of energy equations. And if you solve that equation, you will be able to have some idea, or you will be able to describe the flow around an airfoil. That's the idea, and that's why I will give you some review of conservation equations. Contrary to the conventional way, I will start with the conservation of momentum equation, and then you see here the conservation of momentum equation in the x direction for inviscid flow with no body forces, and under the assumption that the flow is also steady. So first of all, the equation can be written in a form that's shown here on the first line. You have density times material derivative of u component of velocity, that's equal to minus dp dx. Of course, that's the equation in the x direction. So if you write this material derivative in an open form, and then neglecting the first term because we assume that the flow is steady, we end up with the convective terms of the material derivative multiplied by the density, and on the right hand side you have the gradient of pressure in the x direction. So let's multiply everything by dx, and then we end up with the equation that's given on the third line. And now we have here v dx and w dx terms, as you can see here in the second and the third terms on the left hand side of the equation. And now what I'm going to assume that I'm just working along a streamline, such that by using the definition of the streamline, you can write down u dy minus v dx being equal to 0, or for the third, in order to consider the third dimension as well, u dz minus w dx equals to 0. These are actually used in order to calculate the equation of the streamline. You may remember, especially we were actually doing it for two-dimensional cases, and we were writing down dy over dx equals to v over u, because velocity vector is tangential to the streamline at every point along the streamline. So which means that here, instead of v dx, we can write down u dy, so that we can substitute this here with u dy, and instead of w dx we can write down u dz, and instead of these we can write down u dz. And then if you take the left hand side into rho u parentheses, you have rho u times this final summation here, and that's nothing but du, differential of u components. And by using the chain rule, you can actually come up with this. So then eventually you can write down rho u du, that's equal to minus dp dx times dx, or in an alternative way you can write down 1 over 2 times du squared, that's equal to minus 1 over rho times dp over dx times dx. So that's only the momentum equation in x direction, but if you write it down in y and z directions, you will end up with these two other equations that are shown here. So let's sum all of these equations up, so separately left and right hand side, as you can see. So on the left hand side you will end up with 1 over 2 times the summation of these three terms, which is nothing but dv square. V here, capital V here, is the resultant velocity vector, and alternatively you can write it down as 2v dv. And on the right hand side, again, this is nothing but dp here. So then the final momentum equation becomes the momentum conservation of momentum equation becomes here dp equals to minus rho v dv. So this is also known as Euler's equation. So of course this is under the assumption that the flow is steady, flow is inviscid, and we neglect body forces. But I haven't told you anything about flow being compressible or incompressible. So for this reason, this equation holds also for compressible flows. Of course, if you also apply incompressible flow assumption, then you will end up with the Bernoulli's equation. The importance of this Euler's equation is that it relates velocity to pressure along a streamline. So now if I take a step forward and then assume that flow is irrotational, one can show that this equation actually holds anywhere in the flow field. But if the flow is not irrotational, it only holds along a streamline. But if the flow is irrotational, then it holds between any 2 points in the flow. Okay, so this equation is important because of the reason I will actually show you in the coming slide. Because now I will start looking into velocity potential and the continuity equation. So you all remember, I think, the velocity potential here from the aerodynamics 1 classes. So in some cases, I mean, for an irrotational flow, we can assume that velocity can be represented. One can actually mathematically show that velocity can be represented by a gradient of a scalar, and this scalar is known as the velocity potential and represented by phi here. So in that case, u component of the velocity is given by derivative of this velocity potential in x, and then y component of the velocity can be given as d phi over dy, derivative of velocity potential in y direction. Okay, so now let's start looking at continuity equation for a 2D steady flow. So I will just limit myself for the 2D flow to the 2D flow for the sake of simplicity, and then here you have the general form of the continuity equation under the steady flow assumption. And then if you distribute this d over dx to the multiplication terms, multiplying terms here, then you end up with this 4 terms. And my aim now is to write all of these terms in terms of velocity potential, because as I mentioned earlier, my aim is to have one equation that's a combination of all conservation equations, and I will try to do it by only including just one term to be solved, and that will be the velocity potential. So now if you start writing down all of the terms in terms of velocity potential, the first one, du over dx, will be d squared phi over dx squared, the second derivative of phi with respect to x, and u here is d phi over dx, dv dy will be likewise d squared phi over dy squared, and instead of v I have d phi over dy here. But unfortunately I'm not able to write down these density terms in terms of velocity potential, but my aim is again to also find a way to represent them in terms of velocity potential. So I can actually do it by using the conservation of momentum equation, which I derived in the previous slide, because that equation was relating pressure and the velocity. So now if I write down, pressure then in terms of density as well, then I can actually represent I can actually get a relation between velocity and density. So the first thing I start doing is to start with the Euler's equation, write it in this alternative form instead of resultant velocity vector here. As I'm working in 2D, I use u and v square v components of the velocity, and then I can represent them in terms of velocity potentials, as you can see here. Now I have one assumption that was already implied but not said explicitly. My assumption was that it was inviscid flow. As I'm working with velocity potential, then there has to be an assumption of irrotational flow. It's steady, compressible. Now I can assume that this flow is isentropic as well, and in that case dp over d rho is equal to dp over d rho in isentropic conditions, and that's actually equal to square of the speed of sound, which means that I can write down dp as a squared times d rho as shown here. So now if I replace this dp with a squared times d rho, then I end up with this equation. And now if I take a derivative with respect to x, so take a derivative of terms with respect to x on both sides of the equation, then I end up with d rho over dx. That's equal to minus rho over a squared times the terms in the brackets. Okay, so now I have one relation that gives that's actually I have a relation between d rho over dx and the velocity potential, as you can see here. I also need a relation between d rho over dy and the velocity potential again, and you can do the same thing in the y direction, and then you will end up with this equation. Now let's substitute these terms into the equation I had here. So here I had one equation, you may remember. I had here d rho over dx and d rho over dy terms. So if I replace them with their correspondences that I derived here now, and then if I divide everything by rho, because now if I substitute these terms into the previous equation, all of the terms will have rho component. So then if I just simplify, if I divide everything by rho, then I will end up with this equation given in red rectangle here. So that equation is only in terms of velocity potential and the speed of sound here. So I need to do one more thing in order to get rid of the speed of sound, because I just want to have one variable to be solved for this only single equation, and here a square is not a constant, of course, so I need to represent it in terms of velocity potential and some constants if possible. And for that, I'm going to use a form of the energy equation, one form of the energy equation that's actually given here, that you can actually find it in the previous chapters that we saw at the beginning of this semester. So a square can be given as a0 square minus gamma minus 1 over 2 v square. So instead of capital V, again, I can use u and v components, and correspondingly I can use this d phi over dx and d phi over dy terms here. So now I have this equation together with this equation. I can actually, if I solve these two equations, then I can actually get this phi known, because here the only variable is phi, whereas this a square can be represented in terms of phi and a0 square, and for this isentropic flow, a0 is also constant, which means that now when I replace this a square with the corresponding term here, I will only have one variable, that's phi, and if I solve this equation, then I can actually get some important flow components calculated. But the problem is this equation is highly nonlinear, and you need to have really some fancy techniques in order to solve that equation. So in the coming video, I'm going to explain you how we are going to do that.
Okay, any questions up to this point?
Hocam,
Mm-hmm.
I missed the point about A0. What does that mean? I mean,
A0 is square root of gamma R T0, yes? T0 is the stagnation temperature. A0 is the speed of sound at stagnation temperature, yes?
teşekkür
So,
ederim.
since we are dealing with a subsonic flow, first of all, and we are assuming it's an isentropic flow, meaning along a streamline, let's say, that is going to pass over an airfoil, so there will be no heat transfer, and we are ignoring the frictional losses because we assume it's inviscid flow. So therefore, T0 does not change, which makes A0 a constant. So in this equation, A0 is a constant, and all the rest is represented as a function of d phi dx, d phi dy. So basically, and on the left-hand side, it's equal to A square, right? Which appears in this velocity potential equation written in the red rectangle. So if you replace A square here with the expression below, you will end up with a function which you will end up with an expression that is only going to be a function of velocity potential, which is nice because I will have only one variable. But it is, as you will see, maybe in the next video we will see more, but you see that it becomes quite a complicated and nonlinear equation, okay? Let me ask you guys a question. We did similar thing, similar approach for subsonic incompressible flow in aerodynamics 1 class. We derived the velocity potential equation for 2D steady but incompressible flow. That equation was also only a function of phi, function of the velocity potential, but it was much simpler compared to this equation. Does any of you remember that equation? And whether it was a linear or nonlinear equation? So I will let you think for a second. Back in aerodynamics 1 class, we did that.
You asked for velocity, right?
No, we obtained an equation in terms of Laplace. It's a Laplace equation. Well, anyway,
Yeah,
I gave you
just
the
asking
answer.
for...
Yeah, the velocity potential equation, basically, written for incompressible flow, 2D incompressible flow. As I just said, gave you the answer. It was the Laplace equation, if you remember, right? And we did that last semester. And Laplace equation written for phi, it is a linear equation, if you remember. And since it was a linear equation, what did we do? We said we can actually combine different solutions for phi, add them up, and starting from that point, we introduced velocity potential functions, for example, for uniform flow, for sink, for source, things like that. We did that. And we said we could combine these solutions by simply adding them up, because the equation that governs that was Laplace's equation, which is a linear differential equation. Well, it's not the case here. When we start dealing with compressible flow now, because of all the variations in the density, basically, and the derivatives are coming. You can see from, for example, in the slide, we cannot ignore d rho dx, d rho dy. These have to go into the equation, and when they do, they generate a more complicated equation, still only a function of phi, but now it's a nonlinear equation. The question is, how do we solve this one? Because we cannot do what we did for the incompressible case, meaning we cannot just simply start summing up phi solutions, adding them up, and we say, okay, I can generate different complex flow fields just by adding them up. We cannot do that here because we have to do something else because the equation is nonlinear. Okay? So just some more explanation. And let's continue with, let me stop sharing this. Let's continue with the next video regarding this. If I can find it. Okay, the next video. So let me share this one. And let me go to full screen. So can you guys all see the full screen?
Yes, hocam.
Görüyoruz hocam.
Tamamdır. So let's start it.
Okay, now for an irrotational, compressible, steady, and isentropic flow, we managed to get this equation that has only one dependent variable, that's phi. Of course, while saying that, we should consider that we will replace this a square here with the equation given at the bottom of the slide, or we use the second equation, which is the energy equation, in order to have a closure of this problem. Okay, so with these two equations, we can actually solve for phi, and once you get phi, you can calculate many other flow parameters. But before continuing with that, let me remind you again this fact. When compared to our incompressible Laplace equation, this is quite complicated nonlinear equation. So it's not that easy to solve this equation. You really need to use some finite differencing techniques, or you need to simplify this equation. You need to linearize this equation under some assumptions in order to have a solution for this problem. Okay, so what you can do, well, maybe it's better to go through this bullets first of all, before what we can get once you know the phi. So as you can see, this is a single partial differential equation in terms of one dependent variable phi. Reminder again, it's combination of continuity, momentum, and energy equations. You don't need to solve this equation separately. Once you solve this equation given on this slide, once you solve this equation, it's together with this a square a0 square relation, it means that you solve for or you satisfy all conservation of continuity, momentum, and energy equations. And of course you need to have some boundary conditions. You will probably have two boundary conditions. One far field boundary condition, that you assume free stream conditions prevail at far field, and you need to have wall boundary condition where you have normal velocity component being 0. Okay, once you get this phi, you can calculate the other variables as well, like you can take the derivative of phi with respect to s and x, and you end up with the u component. And if you take the derivative of phi with respect to y, you have v component. You can calculate Mach number, and of course our assumption was isentropic flow, which means that also for a calorically perfect gas, for an isentropic flow, you can safely assume that T0, P0, and ρ0 are constant, and they are known from the free stream conditions. So if these are constant and already known from free stream conditions, you can easily calculate static pressure, static temperature, and static density by using the total to static ratio equations for isentropic flows. Of course, as I mentioned, this equation is nonlinear. There is no analytical solution so far, and you need to use some finite differencing techniques. Or you can linearize this equation in order to still get an analytical solution. But of course, in that case, the analytical solution you will get will not be valid for any case that you may consider. There will be some constraints. So Okay, let's start with these two assumptions, which are actually quite familiar to you already because we used similar assumptions when we were working with flow around airfoils in incompressible flows. So we will assume that we have a slender body, slender airfoil, and that airfoil operates at a small angle of attack. Then we will define some perturbation velocities. For instance, for the x component of velocity, we'll have free stream plus some perturbation velocity u hat here, and for the y component, you only have the perturbation velocity that represents the y component of the velocity. That's actually also schematically shown here. That's your resultant velocity component that has both u and v components, and our u component is summation of free stream plus perturbation velocity, whereas our v component is just the perturbation velocity.
Sorry, I would like to make a comment here. Let me go back to this figure here. So basically what we are doing is, since our governing equation, which is the equation that we got in terms of phi, one single equation representing conservation of mass, momentum, and energy, since this is a nonlinear equation, if you would like to obtain an analytical solution, we need to have a linearized version of that equation. And in mathematics, differential mathematics, one way of linearizing equations is using methodology of small perturbations. What does that really mean? It does have a fancy name, but what does it actually mean? It means that, let's say in this case, we have a V infinity, right? Oncoming from left. So by placing a solid body into this free stream, into this flow stream, by placing a solid body, what we are basically doing is we are disturbing this condition, right? We are disturbing this condition. Initially, the velocity, for example, was how is the velocity? We have v infinity along x direction and zero velocity along y direction. But what we do is when we place a body, that body will disturb this condition. How? For example, probably when the streamline is near the body or gets close to the body or over the body, the velocity along x will not be equal to v infinity anymore. What is it going to be equal to? I don't know. But it's going to be different than v infinity. And so therefore it's going to be either v infinity plus something or v infinity minus something. Regarding the y component of velocity, again, initially it was zero, but when the streamline is passing, let's say, close to the body, proximity to the body, well, the y component of velocity may not be zero. It is also going to be disturbed. The thing is, if these disturbances are small enough, which can only be generated if this solid body that is the cause of these disturbances is either a thin airfoil, for example, and when we say slender body here, we mean basically a thin airfoil, or and the flow is happening at a small angle, is operating at a small angle of attack. So under these thin geometry or thin airfoil and plus small angle of attack conditions, the disturbances that will be applied, or here we say also we use the word perturbation, the perturbation velocities will be small. So they will create, the original velocity field, which is v infinity along x and zero along y, will be perturbed a little bit. Perturbed by u hat, amount of u hat at any point p in the x direction, and perturbed by v along y direction. So v hat, I'm sorry, along y direction. So this is called small perturbation theory. So the idea is, and Mustafa Hoca's video will explain it, the idea is if this is the case, we can actually use this condition, small perturbations applied to our velocity field in our equation set, and work out our equation set and keeping in mind that these disturbances are small, we can actually obtain a linear version of our originally nonlinear equation. That's the idea, okay? So let's continue. I just wanted to make this additional explanation here.
Component is summation of free stream plus perturbation velocity, whereas our V component is just the perturbation velocity. Okay. Similar to defining perturbation velocities, you can also define a perturbation potential, because here the velocity is given as a gradient of our potential, velocity potential, and then let's define this velocity potential as v infinity times x plus some perturbation potential. So when you take the derivative of this phi with respect to x, you will end up with of course v infinity plus the derivative of this perturbation potential with respect to x, and that in that case this has to be u hat, that's the perturbation velocity. So if you take the derivative of perturbation potential with respect to y, then you will have the y component of the perturbation velocity v hat. So these are also shown here again, the first derivative of the our velocity potential, and then the corresponding terms in terms of the perturbation potential. And then if you take the second derivative of our of the velocity potential, then it will be equal to the second derivative of the perturbation potential, and the cross derivatives are also similar in the same sense. So now let's use the equation that we derived at the end of the first video, and then instead of using the velocity potential only, let's use perturbation potential. So what I mean here is that, so let's go back a couple of slides back. So instead of phi here, let's use u infinity times x plus phi hat, and then let's then use the corresponding derivatives, the first and the second derivatives, instead of using just the velocity potential itself. So then if you do so, then this is the resultant equation you will get, but still now it's of course in terms of perturbation velocity potentials, but still it's non-linear, so we haven't still linearized that. Let's take a couple of steps forward. So let's write now this equation in terms of perturbation velocities, because here in the previous slide you have this perturbation velocity potentials, and then if you replace them with their corresponding perturbation velocities, then this is the final equation you will get. We do the same thing also for the energy equation, as you can see here, and this is the final equation you will get. Now we have again these two equations that needs to be solved in order to get your flow components. Okay, now let's write the speed of sound in the first equation in terms of the speed of sound at free stream conditions. So let's replace this a square with these three terms here, and then reorganize this final equation in order to end up with this, as you can see here. So this is actually rearranged on purpose in this manner, because now you have, you know, similar derivative terms on both sides, the u hat over the x, the u hat over the x, times some terms in brackets, then dv hat over dy. Again, on the right hand side of the equation you have a similar term, and then finally you have this final term here. So it's still nonlinear. We haven't still done anything yet, so still exact for an irrotational isentropic flow. Now it's time to do some simplifications under the assumption that we are working with a slender body and the angle of attack is small. Okay, first of all, because of these two assumptions, we may assume that the perturbation velocities are very small, especially they are very small compared to the free stream velocity. Because of this, u hat over v infinity and v hat over v infinity are much smaller than 1. And of course their squares will be even much smaller than 1. So by taking this into account, we can actually go term by term and see what are the contributions of each term on both sides of the equation. First of all, let's start with the first term on the right hand side. So we had this Mach infinity squared times some terms in brackets, in square brackets, times du hat over dx. So for Mach number between 0 and 0.8 and for Mach number greater than 1.2, this term is smaller compared, this term is relatively small compared to the du hat over dx term on the left hand side of this equation. So what I mean here, let's go back again. So this term here is much, it's smaller than this term here. Okay, so in that case we can actually neglect this complete term on the right hand, complete first term on the right hand side. If you look at the second term again, which is this one, and then if you compare it with the with 1 here, so it's actually also, if your Mach number is smaller than 5 approximately, then this term is small compared to dv hat over dy. Okay, so this then can be safely neglected, and then eventually you have the third term here, and that third term, because of, again, you know, small perturbation velocities, is very close to 0 as well, such that it can be also neglected. So if you do all these simplifications, then the equation becomes this: 1 minus Mach infinity squared times du hat over dx plus dv hat over dy, that's equal to 0, because we only end up with the left hand side terms, and all the right hand side terms can be neglected. So this can be written in terms of perturbation potential, velocity potential, of course. Instead of du hat over dx, we can write down d square phi hat over dx square, and likewise for dv hat over dy, then we can write down d square phi hat over dy square. So this is now linear but not exact. So our assumption is that it's only valid for small perturbations, which means that you have to have a slender body, thin body, and a small angle of attack, and it's only valid for subsonic or supersonic flow. It's not valid in transonic or hypersonic regimes. That's because you may remember that in the previous slide these terms become very small, especially if you are outside of, if you are within this range, for instance, for the first term, and for the second term, this is only valid, so this is only small if your Mach number is smaller than 5. Okay, for this reason, it's not, this potential equation is not valid in transonic or hypersonic regions. Well, okay, at the end of the linearization process, we ended up with this linear equation.
I think we automatically started the third video, which is a continuation of this. Let's continue for a few minutes, and then we have 5 minutes left. Then we will stop. Okay.
With one dependent variable, that's phi hat, that's the perturbation velocity potential. Of course, this is not an exact equation. It's only valid for small perturbations, which means that slender bodies at small angles of attack, and it's only valid in subsonic and supersonic flows. It's not valid in transonic and hypersonic regimes. Well, after having this equation, there is one other important flow parameter that we may be interested in, because we would like to eventually get lift and moment coefficient applied on the body on the object in the flow, and in order to get that, we need to, of course, you may remember already from aerodynamics 1 classes, we need to integrate the pressure coefficient. So here the pressure coefficient is defined as in a conventional way as static pressure minus static pressure of the free stream flow divided by the dynamic pressure. Well, the dynamic pressure can be represented in terms of Mach number by using the definition of the speed of sound. And once it's represented in this way, and then this dynamic pressure definition can be plugged into the static pressure equation here, and then the resultant equation would be this one shown in red rectangle here again. Of course, this is the pressure. This is an exact definition of the pressure coefficient, but it's only in terms of the Mach number. And from now on, let's start using the assumptions that we had for our specific flow case. You may remember that we were dealing with adiabatic flow of a calorically perfect gas, which will allow us to write down this relation between static temperature at a point of interest and the static pressure, static temperature of the free stream. Of course, while doing that, my aim is to now get a relation for P over P infinity, and then write this actually in terms of perturbation velocity or perturbation potential, because from the equation that we derived here, we will end up with the perturbation velocity potential. Now, if I can represent the pressure coefficient in terms of the perturbation velocity potential, I can easily calculate the pressure coefficient once the other equation is solved. Okay, so writing down this equation using the definition of Cp and rearranging this equation, I will end up with, this T over T infinity is equal to 1 minus gamma minus 1 divided by 2 over A infinity squared times some terms that are associated with the perturbation velocities. Just a small correction here. The resultant velocity vector here only is the x component is given, but there should be also y component, which will be the v hat square here, because once this is plugged in here, then you can then end up with this relation. Okay, in addition to having this adiabatic adiabatic flow of a calorically perfect gas, that the flow of interest or the flow case that we are particularly working in is also irreversible, which means that the flow is then it's reversible, so that the flow is then isentropic, which means that you can use the relation between T over T infinity and P over P infinity as shown here. Okay, so then we already have T over T infinity here, and then if you plug that in here, having this relation for an isentropic flow, we will end up with this equation. That's still an exact equation. Of course, we haven't done any simplification yet, but we just said that it's valid for isentropic flow case. Okay, now we have these terms in brackets, and as you can already see here, we have u hat over v infinity, which is rather small because of assumption of small perturbation velocities, and we have u hat square plus v hat square divided by v infinity square. That's even smaller than the first term, probably because you have the squares here, squares of the perturbation velocities. And as a result, we may end up with the fact that this complete term is very small if perturbations are small, which actually is the case because we already from the beginning of linearized theory we assume that our perturbations are small. That's actually the basis of our derivation here. So instead of this term, let's use the symbol epsilon here, and then this P over P infinity equation then becomes can be represented in this simple way. So now let's use binomial expansion instead of using this exact equation, and of course in that case you will have some high order terms of epsilon here, and because epsilon is already small, its powers are also quite small. Then we can neglect actually high order terms, and neglecting high order terms in this binomial expansion of the P over P infinity term, and also neglecting these terms here, we end up with one simple CP definition that's actually shown here. Here the pressure coefficient is only a function of your perturbation velocity in the x direction and your free stream velocity. Okay, we actually have this, and as you can see, this u hat can be directly.
Okay, I think it's a good point to stop here. As you have seen, for the linearized theory, we obtained first of all a governing equation, and also a relation for the pressure coefficient, simple relation for the pressure coefficient over on the body, on the thin airfoil, written in terms of the perturbation velocity along x, and it's basically the ratio of perturbation velocity along x to v infinity. So quite easy to calculate the pressure coefficient if you actually, if you can solve that phi equation for the perturbation velocity potential, you get phi hat, you get derivative with respect to x, you get u hat. This means that you automatically obtained CP distribution on the airfoil using the u hat distribution around the airfoil. So we will continue from this point next week, okay? Regarding the subsonic compressible flow or airfoils up to Mach 0.8, basically, outside the transonic region. We will deal with the transonic region later on in the coming days. Any questions?
Hocam, did you decide on how we will conduct the exam?
Exam will be online.
Yep. Up to which topics you are responsible?
Until yesterday, so until end of the converging diverging duct. Today's topics will not be included.
Teşekkür hocam.
Hocam, is it going to be closed notes, and are we allowed to prepare formula sheets?
It's going to be closed notes. If you need any formula, we will provide them.
Okay, thank you.
Any other question? Okay, thanks very much. I have another meeting and I really need to go. Thanks very much for attending today. And we will see each other, we will talk to each other again next Wednesday, okay? And I guess we have a midterm before that. Good luck with the midterm. And I'll see you on Wednesday.
İyi günler hocam. Dikkat edin kendinize.
İyi günler. Teşekkürler.